Hi everyone, I am Kiranmai. Welcome to my channel Chemistry Tutorials by Kiranmai. In last video, we discussed about the models of atom proposed by Thomson and Rutherford, and we also discussed the drawbacks of these atomic models. Today in this video, I am going to discuss about the developments leading to Bohr's model of atom. Overcoming the drawbacks of Rutherford's atomic model, Niels Bohr proposed his Bohr's model of atom. It is an improved version of Rutherford's atomic model. Two developments played major role in the formulation of Bohr's model of atom. Those two developments are: one is dual nature of electromagnetic radiation, and second is experimental results regarding spectra. Dual character of electromagnetic radiation means electromagnetic radiation's nature. Dual means two. Electromagnetic radiations have two natures. One is wave nature and other is particle nature. So scientists discovered that electromagnetic radiations have wave nature and particle nature. And another development is regarding atomic spectra. We will discuss it in detail one after the other. First one, in today's class we are starting the explanation for real character of electromagnetic radiation. In this class I am discussing about wave nature of electromagnetic radiation. Wave nature of electromagnetic radiation. Before going into this topic, I would like you to know about the meaning of few terms like acceleration. The word acceleration means rate of change of velocity. So here acceleration means rate of change of velocity. Acceleration means rate of change of velocity. Again, velocity means the speed of something in a given direction. Velocity means the speed of something. Here something means about which we are talking about. Something, if we are talking about atoms, it is the speed of atom. The speed of something in a given direction. In a given direction. The speed of something in the given direction. See, velocity means speed plus direction. Velocity is a vector quantity, means it has both magnitude and direction. So if we refer to the velocity, we must consider speed as well as the direction. If speed changes, velocity changes. If speed remain constant and direction changes, then also the velocity gets changed. So here acceleration means rate of change of velocity. Velocity means speed of something in a given direction. So let us consider one example. Car picks up its speed from rest to 20 kilometers per hour in 5 minutes. So car is in rest and it picks up the speed of 20 kilometers per hour in 5 minutes. In these 5 minutes, from 0 to 5 minutes. In these 5 minutes, you can see the speed is continuously changing. So, speed is changing. Speed changing means there is a change in its velocity. So, whenever there is a change in velocity, there is acceleration. So, as the speed changes, velocity changes. So, it leads to the change in velocity. So, there will be an acceleration. Consider another example. Suppose the car is moving with 20 kilometers per hour. It is taking turn. In this time also the car is maintaining 20 kilometers per hour and again it is moving with 20 kilometers per hour. So you can see constant speed in car while it is traveling. Here also the velocity gets changed because the direction of car is changed. Though its speed is constant, direction changes. So when there is a change in direction, velocity changes. So where the velocity changes, there will be acceleration. So here also velocity changes, it leads to acceleration. Hope you understood the meaning of acceleration. Acceleration means rate of change of velocity. Velocity means speed of something in a given direction. If speed changes or direction changes, which causes the change in velocity. So, acceleration exists when there is a change in velocity. So, keep this one in mind. So, let's proceed to the topic wave nature of electromagnetic radiation. First, James Maxwell suggested that when electrically charged particle electrically charged particle moves under acceleration moves under acceleration moves under acceleration alternating electric and magnetic fields are produced. Alternating electric and magnetic fields are produced and transmitted. Or transmitted. Produced and transmitted. See, when electrically charged particle, You all know that the subatomic particles which are in motion according to Rutherford are electrons. So he said that there will be nucleus in an atom, nucleus, and the electrons will be revolving round the nucleus. So here electrons are charged particles, electrically charged particles. So electrons are negatively charged particles. When these particles moves under acceleration, so here suppose with the same speed electrons are revolving round the nucleus, means its direction is continuously changing. Though the speed is same, its direction gets changed. So its velocity gets changed. So when velocity gets changed, it will be under acceleration. So when electrically charged particle moves under acceleration, so these electrons moves around the nucleus, produces electric and magnetic fields, and these fields are transmitted. These fields are transmitted in the form of waves. In the form of waves. These waves are called electromagnetic waves. Electromagnetic waves, or these are also known as electromagnetic radiations. Electromagnetic radiations. Again I am repeating, when electrically charged particle moves under acceleration, alternating electric and magnetic fields are produced and transmitted. They are transmitted in the form of waves called electromagnetic waves or electromagnetic radiations. Hope you understand this one. And Maxwell was again the first to reveal that light waves are associated with oscillating electric and magnetic character. So, light waves are associated with oscillating electric and magnetic character. See, oscillating means varying in position. Vary in position means change in position in a regular manner. Regular manner about a central point. Means it is oscillating up and down or back and forth at a through a central point, oscillating. So light waves are associated with oscillating electric and magnetic character. Means light waves have electric and magnetic character. So Maxwell proposed that electrically charged particle produce electromagnetic waves, and he is also the first scientist to reveal that light waves have electric and magnetic character. So let's see what are the properties of electromagnetic waves. Properties of electromagnetic waves. First property, oscillating electric and magnetic fields are produced by oscillating charged particles are perpendicular to each other and both electric and magnetic fields are perpendicular to direction of propagation of wave. So here charged particles when they are oscillating produce oscillating electric and magnetic fields. These fields, electric and magnetic fields, are perpendicular to each other. See, the oscillating charged particles produce electric field in this direction and magnetic field in this direction. Both are perpendicular to each other. And then these two, electric and magnetic fields, are perpendicular to direction of propagation of wave. So let the wave be propagating in this direction. Then the electric field will be in this direction, 90 degrees, and magnetic field will be in this direction, oscillating. This is also 90 degrees and this one is also 90 degrees. So you can see mutually perpendicular to one another. So let's see the graph. If we take x-axis, y-axis and z-axis, 3 coordinates. In x-axis, let's be the direction of propagation of the wave. Direction of propagation of wave be in x-axis, and in z-axis, electric field will be oscillating like this, perpendicular, and in y-axis the molecules are oscillating in this direction. Means here the direction of propagation of wave, electric field, magnetic field, all are mutually perpendicular to one another. This is the first property of electromagnetic radiations. And second one is electromagnetic radiations do not require any medium, that is they can travel in vacuum. So see, do not require a medium. So they do not require any medium for propagation. They can freely propagate in vacuum. That is, they can move in vacuum. You all know that sound requires a medium to travel. Any liquid or solid or gas, any medium is required for movement of sound waves. But here, electromagnetic waves do not require a medium. Do not require a medium. Next, third property is there are many types of electromagnetic radiations. Many types of electromagnetic radiations. These types, which differ from one another, by which they differ from one another, is wavelength. What is wavelength and all I will be discussing now. So remember that there are many types of electromagnetic waves, and these waves are differ one another with the wavelength. So simply you can say that depending on the wavelength, electromagnetic radiations are many types. Depending on wavelength, electromagnetic radiations are many types. See, these electromagnetic radiations, when they are kept in order, it is known as electromagnetic spectrum. So different regions of spectrum are identified by different names. See, in electromagnetic radiations are many types depending upon its wavelength or depending upon its frequency. What is meant by wavelength, what is meant by frequency, I will be discussing now. Now you just remember that depending on wavelength, electromagnetic radiations are many types, and they all fall into an electromagnetic spectrum. Electromagnetic spectrum. Electromagnetic spectrum. This spectrum is classified or divided into different regions based on the wavelength or frequency of the radiations, such as radio waves, microwave waves, infrared, visible, ultraviolet, X-rays, gamma rays, like that. X-rays and gamma rays. So radio waves, microwaves, infrared waves, visible rays, ultraviolet, X-rays, gamma rays. Radio waves frequency region will be around 10 power 6 Hz, and this is the frequency which we use to broadcast the radio. And microwave radiations will have the frequency of 10 power 10 Hz. Infrared rays will be 10 power 13 Hz. Visible, which our eyes can see, fall around 10 power 15 Hz. Ultraviolet 10 power 16 Hz. Like that, the frequency will be increasing. So to remember this order, there is one mnemonic. Remember this sentence and you will get to know this order. The mnemonic is: rich men in Vegas use expensive gadgets. Remember this sentence, and the first letter of each word in this sentence gives us the type of region in electromagnetic spectrum. See, radio waves, microwaves, infrared waves, visible rays, ultraviolet rays, X-rays, gamma rays. Okay, these regions are specific, or we can say that each region have a different wavelength corresponding to electromagnetic radiations. So different kinds of electromagnetic radiations falls in the electromagnetic spectrum. Okay, now let's discuss about the properties of electromagnetic radiations, or the characteristics of electromagnetic radiations. See here, different units are used to represent electromagnetic radiations. Different units are used to represent electromagnetic radiations. See, I can say that some 500 wavelength electromagnetic radiations, 60 hertz electromagnetic radiations, or the wave number 6 electromagnetic radiations, like that we will be saying. Means different units like hertz, meters, centimeter inverse, like different units are there to represent electromagnetic radiations. These units correspond to particular property exhibited by electromagnetic radiations. So first one, frequency. So frequency, it is denoted by the symbol mu. And what is the frequency? Means the number of waves that pass a point in 1 second. Number of waves that pass the given point in 1 second is known as frequency. The number of waves that pass a given point in 1 second, in 1 second is known as frequency, and frequency is represented by the SI unit hertz. And second one, wavelength. See, let's consider this one as a wave. The distance between two successive crusts, this one is crust, this one is trough. The distance between two successive crusts, or the distance between two successive troughs, is known as wavelength. The distance between wavelength. And then the units of wavelength are meters, and it is represented by the symbol lambda. represented by the symbol lambda. So wavelength is the distance between two successive crusts or two successive troughs. And the other one is important point: electromagnetic radiations, regardless of wavelength, travel at the same speed in vacuum. So in vacuum, the speed of electromagnetic radiation. See here, electromagnetic radiation, whatever its wavelength may be, in vacuum, the all radiations show the same speed, that is speed of light. Speed is equal to 3 into 10 power 8 meters per second. It is actually 2.997925 into 10 power 8 meters per second. So as it is 2.997, we are taking it as 3 into 10 power 8 meters per second, which is the speed of light, represented by C. So frequency, wavelength, speed are related by the equation. So frequency mu, wavelength lambda, and speed c are related with the formula c is equal to mu into lambda. So this is an important equation. Please do remember this one. C, speed of electromagnetic radiation is the product of its frequency and wavelength. And another important one which we will be using is wave number. Wave number. So wave number, it is represented with mu bar, and it is defined as the number of wavelengths per unit length. The number of wavelengths per unit length. See here, if you take a unit length, the wave is passing like this. This is wavelength, distance between two successive crusts or troughs. Distance between two successive crusts or troughs is wavelength. So number of wavelengths present in unit length is known as wave number. Its unit is meter inverse. Generally we will be using the unit centimeter inverse for this. Generally we will be using centimeter inverse. So these are the terms: frequency, wavelength, speed, and wave number, which we will be using for electromagnetic radiations. So these wave nature of electromagnetic radiations can easily explain diffraction and interference. Experimental phenomenon such as diffraction and interference can be easily explained by wave nature of electromagnetic radiation. So let's discuss about what is meant by diffraction and what is meant by interference, how the electromagnetic radiation explains these two phenomena. So first one, diffraction. First one, diffraction. Diffraction means bending of waves around the corners of an obstacle or through an aperture into the geometrical shadow of obstacle or aperture. So let me explain. Um, if you place an obstacle in the path of light, you can observe some sort of shadow, right? But if there is, and there will be a light here also, it will not be a complete darkness, but you can feel some light. Similarly, if you incident some light with a card with small aperture in it, actually there must be a dark shadow, that is absence of light here. But when a light passes through this aperture, you can feel some light here also. So this is mainly due to diffraction. Okay, this is mainly due to diffraction because the light rays bend here, they will bend around the corners of an obstacle, and they will move through the aperture into geometrical shadow. Here geometrical shadow means the shadow that would have been cast if diffraction effects doesn't happen. If the diffraction doesn't exist, we can see clear dark shadow, but we cannot see in practice, you cannot see the dark shadow. You can feel some light, presence of some light in the shadow. This is due to diffraction. So let me explain again. See, bending of waves around the corners of obstacle or through the aperture into geometrical shadow of obstacle or aperture. So here what is meant by geometrical shadow means the shadow the shadow that have been cast that have been cast if diffraction doesn't occur. If diffraction doesn't occur. So see, if diffraction doesn't occur, it should be in dark color. But if we place any object in the path of light, it will not, the shadow of it will not be that much dark. You can see or you can feel the presence of light in that shadow. This phenomenon, this is because of bending of rays around the corner of the obstacle or through an aperture. This phenomenon is known as diffraction. See, this phenomenon of diffraction can be explained only when the light rays or electromagnetic radiations have wave nature. See, the wave is passing like this. Actually, like this. From sideways, if from the above plane of paper, you see like lines. If we see from the plane of paper, means from this angle, it will be like this, up down up down up down. The wave is passing like this. When it touches or an obstacle with a small aperture in it. What we predict is there will be a shadow here, except here there will be shadow in this area. But actually what happens is these light rays, after passing through the aperture, they bend. So you can feel the presence of light even in this area. This is all because when the light ray bends, every point on the crust, every point on the crust actually acts as a source of light. So from here again the radiations gets started, secondary propagation we say. Due to this phenomenon only you can see the light in this region. This phenomenon can be explained only when the radiations have wave-like nature. Hope you understand this diffraction. Next, moving into the another one phenomenon, interference. Interference. See, what is meant by interference means this is a phenomenon in which two waves, A, B, in which two waves superimpose on one another. Two waves superimpose on one another to form resultant wave with greater or lower or the same greater or lower or same amplitude. So the resultant wave will have greater amplitude or lower amplitude or the same amplitude. Again the term amplitude. Amplitude means if we consider this one as a wave, the distance between the highest point of crust to this middle line, this one is amplitude. The maximum distance moved by a point on a vibrating body of a wave from its equilibrium position. So highest point nunchi high from highest point to equilibrium, the distance measured is known as amplitude. So when two waves superimpose on each other and that gives a resultant wave with a greater amplitude or lower amplitude or the same amplitude, this phenomenon is known as interference. This one is also explained only when the electromagnetic radiations have wave-like properties. So about two phenomena, that is diffraction and interference, is explained only when the electromagnetic radiations have wave-like nature. So some of the observations also suggest that electromagnetic radiations may not have or may not only have wave nature. See, black body radiations, photoelectric effect, heat capacity of solids, line spectrum, especially when referred with hydrogen, cannot be explained by considering only wave nature of electromagnetic radiations. This one I will be explaining in the next video. black body radiation, photoelectric effect, heat capacity of solids, and then line spectrum with special reference to hydrogen atom. These one and all, these experiments or these observations are not explained when electromagnetic radiations have only wave nature. So, these observations can be explained only when we consider electromagnetic radiations have particle nature. I will be discussing these topics in the upcoming videos. So, in this video, we discussed about the wave nature of electromagnetic radiations, which is the main development which led to the discovery of Bohr's atomic model. So in this class we discussed about the wave nature of electromagnetic radiations and properties of electromagnetic radiations, and then few units or the properties like frequency, wavelength, wave number and all we discussed, and the experimental phenomenon such as diffraction and interference we discussed in this video. If you have any doubt in these topics which I have explained in this video, please comment in the comment box. And if you like this content, like this video and share with your friends who are interested in studying chemistry. Thank you.